Welcome back. So we will start this next lecture of the lecture series about this fiber optic laser source. And in the last lectures, we have explained about the different types of LEDs, and also we have explained this basic principle of these lasers and the different types of lasers like gas lasers and semiconductor lasers and distributed feedback lasers, and so on. Now, we will continue our lecture with this laser diode characteristics. And this is something similar to the characteristic which we have discussed for these light emitting diodes. And if you will see this slide, let me just make full screen. So, uh, this is actually the current versus power characteristics, or the voltage versus the power characteristics for this laser diode. And if you will see this characteristic here, then you can notice that this laser diode is not perfectly linear, because there is small amount of optical power when this current is up to this value, like 60 milliamps. And after that, this current the optical power suddenly rises. So therefore, you can expect a linear behavior in this range. Whereas this is again another region. So if you will consider the total graph, then it is noticed that this is not perfect linear. So therefore, the linearity of laser diode is not as good as this light emitting diode. Now, coming to this modulation behavior, as you have also discussed for this light emitting diode. So because the pronounced linear behavior is obtained in this region, so therefore this linear region can be used for the modulation of the source or the laser diode. Now, because I have to use this linear region, therefore I have to use a current source even for digital modulation. And therefore, in the circuit, you have represented this current source IDC. And this source is used to take this operating point from the origin to the point somewhere here, so that this signal at the input will be along this linear region. Now, if you want similarly the analog modulation, the IDC value will be something more than the IDC value which is given in this particular situation. Because if this ITC value is maintained with the same value as in case of digital modulation, then the negative half cycle will come out of this linear region, which we do not want. So therefore, if you want digital modulation, again, you have to use a DC current source, but the magnitude of DC current source, which is required for this analog modulation in case of laser diode, will be something more than the value of IDC, which is required for this digital modulation. So this is all about this digital modulation, and you can compare this, digital modulation, the modulation for this LED and this laser diode in this slide. So as you can see, this is perfect linear, whereas this is not perfect linear. Therefore, you are using this portion of this graph for this modulation of LED, whereas here you are using this portion of the graph for this modulation of LD. Now, one of the demerit of the laser diode is that the characteristic which we have mentioned is temperature dependent. That means, as you can see, the threshold value of current after which there is a shoot in this optical power varies with this increase in temperature. For example, for 30 degrees centigrade, this threshold power, threshold current is somewhere here, and for 40 degrees centigrade is somewhere more, and this increases as the temperature increases. So this is not the case in case of the light emitting diode. So therefore, light emitting diode, the characteristic is temperature independent, whereas in case of laser diode, this is temperature dependent. So this is in fact a demerit of this laser diode. And this is again the frequency response. As you can see, the modulation frequency is somewhere here, and the relative intensity remains in fact flat up to this region. That means this is actually the region where you can use this modulation, and the modulation will be faithful in this region. And the modulation will not be proper if the frequency is more than this value. That means uh, if the frequency of the signal is more than maybe 2.8 gigahertz, then there is a problem in these modulations. And this is about this LD mounting, as you have discussed in case of LED. Some coatings or some protecting seeds should be given to this LD so that it will be protected from this external environment. And this is what is called the packaging. And this is another way of packaging or the mounting of this LD. And finally, we will try to distinguish between this, emission from this light emitting diode and this laser diode. And in this context, I have presented here the radiation from this edge emitting LED, and this is the surface emitting LED, and this is actually your laser, your edge emitting LED. Now, if you'll see this radiation from laser diode, then this says that there will be two different plane because this laser diode is something similar to the edge emitting LED, as I mentioned in my last lecture. So there is a distribution of intensity in the parallel plane, and the distribution of intensity changes in this perpendicular plane. And as you can see in the parallel plane, this distribution of intensity is something like this, where the FWHM is 10 degree, whereas for this perpendicular plane, this FWHM is something 35 degree. In contrast, if you will see this, light emitting diode, this parallel plane is somewhere here. So as you can see, the light emission is more narrow, okay, in case of your parallel plane, in case of your laser diode, whereas the light emission is broader in case of your LED in the parallel plane. So this is just the reverse trend which you are getting. And another reference you can mark here is though the light radiation is narrower in the perpendicular plane here in case of your LED, but this FWHM is 30 degree compared to this FWHM 10 degree here. That means you can get more narrower laser beam, light beams in case of laser diode, right? So this is how you can distinguish between the radiation pattern between this light emitting diode and this laser diode. So these are other configurations of laser diode. We will just mention but not go into detail. This is called the vertical cavity surface emitting laser diode, where a cavity is formed between this upper surface and the lower surface by using some grating-like structures as reflectors. So the active region is here, and one reflector is corrugated here, another reflector is corrugated here, so that this will act as a cavity. And this vertical cavity surface emitting laser diode will give, in fact, very powerful laser beams, because the cavity resonance will take place, and therefore the emission power will be enhanced. So with this, we come to an end for these light sources. In fact, the fiber optic light sources. Another important component in the fiber optics is the detector, the light detectors. That means the light which propagates in this optical fiber is to be detected by some devices, and this is the detector which will detect the light. In fact, this is called as the photo detector, because it has to detect the light signal. So again, you have to understand what are the requirements for an optical detector. And we have mentioned some of these requirements for this optical detector. The first requirement is high sensitivity at this operating wavelength. That means if you want to detect a particular signal, then what is important here is to know what is the wavelength you want to detect. For example, a detector which is sensitive to 650 nanometer may not be sensitive to maybe 1300 nanometer. So depending on this wavelength, you have to choose or you have to select this detector. So the detector which you are using should be very sensitive to the wavelength which you want to detect. The second requirement is high fidelity. That means the detector should be capable of receiving the signal easily. Then the large electrical response to this optical signal, because finally this optical signal will be converted to electrical signal. Then short response time. Uh, it is obvious, because when you will put the light signal onto the detector, then the optical power will be converted into this electrical power, and the time for the conversion should be as small as possible. And there should be minimum noise in the detector. There may be different types of noise which you can see later. So the noise should be also minimum in this detector. And the other criteria are obvious in any device, like stability, then small size, low bias voltage, high reliability, and low cost. So these are the requirements for this optical detectors. Now, with this background, let us try to understand. So, what are the different photo detectors which are available for the detectors detection of light? Now, here I have mentioned some of the devices which are used for this photo detection. And in this context, I can mention this photo multiplier, then the semiconductor photodiode. Basically, this is the pin, and the avalanche photodiodes. So we will try to understand these different photo detectors one by one. But before that, let me go to this principle of photo detection and some basic definitions which we will use when we will go to explain this principle of photo detection and the working of these photo detectors. So the first definition, or the term which you have to understand, is what is known as the quantum efficiency. Now, what is this quantum efficiency? As you can see, this is the ratio of the output electron number to the incident photon number. Because what happens in a detector, the detector receives this optical signal and converts this into electrical signal. And therefore, the incident is you can say in terms of photon number, and the output is in terms of this electron number. So therefore, if you will want to find the efficiency, then it should be a ratio between this output and the input. And therefore, the output here is the electron number, and the input is the incident photon number. So the ratio will give the quantum efficiency. Similarly, the responsivity The responsivity is again decided by this ratio, this I divided by P in. This is somewhat related to this, quantum efficiency. So this is in fact the ratio between this photocurrent and the input optical power. And the bandwidth or the rise time, which we have discussed while discussing this, LED. So F3dV is equal to 0.35 TR. And finally, the term which we are discussing is the dark current. Dark current, it is in fact the current which is generated in this detector, even in the absence of the input optical power. So there may be some ambient light which is present in the surrounding, and due to this, there may be some small, detector current which may arise, and this is called as the dark current. Of course, this receiver this detector is one component of this receiver, and if you want to have a receiver in this optical communication system, then it would have a detector, then the amplifier, then this thresholding and all. But just to give a feeling that the receiver is not only the detector, but detector with some other electronic components. Now coming to the basic principle of photo detection. Uh, Again, we have to go back to this light material interaction, which you have explained in my last lectures. So when light interacts with matter, then there is absorption, and also there will be emission, and there will be spontaneous emission. So when you have this, you know, the laser. The laser is based on this stimulated emission. Similarly, LED, we have said that this is based on the spontaneous emission. Now, then what is the principle of photodetector? The principle of photodetector is absorption. That means the photodetector will absorb these photons. So when this photodetector will absorb this photon, then what will happen is basically there will be either release of electrons or release of creation of electrons and holes. For example, if you will take a metal surface and if you will incident light onto this metal surface, then the electrons can be ejected from this metal surface. So the amount or the number of electrons which will be ejected from this metal surface may be related to the amount of light which is incident, and therefore if you can measure the current which is flowing due to this electrons which is ejected due to this light which is incident on the surface, then you can correlate between the light and the current, and this is how you can detect the light or which is incident on a particular surface. So based on that, there may be two different types of photodetectors, and this classification is based on the principle like external photoelectric effect and internal photoelectric effect. When I say internal external photoelectric effect, this is basically which will take place in vacuum photodiode and photomultipliers. And when I talk about internal photoelectric effect, then this will happen in PN junction photodiode, PIN photodiode, and the avalanche photodiode. Now, the basic difference between this external photoelectric effect and internal photoelectric effect is that in external photoelectric effect, really the electrons are separated from this metal surface. Whereas in case of internal photoelectric effect, the charge carriers like electrons and holes are not really separated from this material surface. They are inside this material surface. So when you will shine light onto a metal surface, for example, the electrons are ejected out, and this is your external photoelectric effect. Whereas if you will shine a light to a semiconductor, then the electrons and holes are produced, but they are not coming out of this material. Therefore, this is internal photoelectric effect. So therefore, the principle of photodetection can be classified based on whether you are measuring the current by taking this principle like external photoelectric effect, or you are using a principle which is known as internal photoelectric effect, where the conduction is due to these electrons and holes. So to start with the external photoelectric effect, let us try to understand the basic principle by using what is called as a vacuum photodiode. Now, in this diagram, which what I have shown is two electrodes. One is the cathode, another is the anode, and the light is incident on this cathode. So as a result of photoelectric effect, the electrons will be ejected out of this cathode. And if you will make this anode here and it is positive with respect to this, therefore the electrons will be attracted towards this anode, and finally the current will flow in this external circuit. So therefore, the current which will flow in this external circuit is directly proportional to this light which is incident on this cathode. So therefore, based on this, you can measure the amount of light which is incident on this cathode. So this may be the basic principle by which you can measure this light, or the amount of light which is incident on this cathode or on any material. So then, what is the problem with this vacuum photodiode? So when you will shine light to this cathode and you will try to measure the current, then you will find that unfortunately there will be no current which will be measured in the external circuit. So this means that that there may not be electrons which are ejected out of this material, or if at all the electrons are ejected out of the material, the number of electrons are so small that the current which is flowing in the external circuit is very, very small, and therefore you are not able to measure that current. So to avoid this problem, there is another detector which was proposed, which is known as the photomultiplier. Now, what is this photomultiplier? This photomultiplier is the same configuration as that of the vacuum photodiode, but the only difference is you place some denodes in between these two electrodes, that means cathode and anode. So these lines which I have represented here are known as the denodes, some of the electrodes. And what is the role of this denode here? For example, when this incoming light is incident here, then the electrons are ejected out. Now, as I said, if this number of electrons is less, then the current which will flow in the external circuit is very less, and therefore it may not be detected by this ammeter or milliammeter or whatever. But if I can increase this number of electrons when it reaches this anode, then I can measure this current easily. And this is the goal of this photomultiplier. So when you will use this dnode, these three electrons which will be emitted from this cathode will be colliding with this dnode and will knock out many electrons from this dnode. For example, they will knock out these three electrons, therefore you will get 6 electrons. So therefore, you are getting 6 electrons out of 3 electrons, and then these 6 electrons will be again accelerated towards this dnode and will be colliding with this dnode and will knock out further electrons. So therefore, when this electrons will get collided with the different electrodes, then the number of electrons which will be ejected out will be increasing, and finally, when they will come out here, the number of electrons will be much more than the number of electrons which are ejected here from this cathode. And therefore, you can increase the current, because now you have increased this number of electrons. Therefore, you can increase this current and can be easily measured in this external circuit. So this is the purpose why this photomultiplier was proposed or invented. Now, if we compare this vacuum photodiode with that of photomultiplier, then the gain which we'll get in case of this photomultiplier can be expressed as something like this. This m is equal to delta to the power n. So delta is in fact the gain which we'll get for the each denode. So if you have n denodes and delta is the gain at each denode, then the total gain which we'll get is something m is equal to delta to the power n. And the total current which we'll get here is something related to this m, which is delta to the power n. So this is M into eta EP divided by HF. In fact, this is your current for vacuum photodiode. If you talk about a photodiode, simple vacuum photodiode, the current which will flow is something eta EP divided by HF. And if you have gain M, then the current will change to a value M into eta EP divided by HM. So what I'm saying is, if you have a very small current which is produced in a vacuum photodiode, then this current can be increased by a factor of M, where M is equal to delta the triple N in case of a photomultiplier. So this is actually the beauty of a photomultiplier. Simply by using some denotes, some electrodes in between two electrodes, then you can increase, in fact, the number of final electrons which will flow in this external circuit. Unfortunately, this photomultiplier cannot be used for the range of wavelength which is used in your optical communications. For example, when you are using this wavelength in second window or third window, like 1310 nanometer or 1550 nanometer, then you cannot use this photomultiplier, because with this amount of energy, your no electrons will be ejected out of this metal surface. So therefore, if no electrons, then this electrons number cannot be multiplied. Electrons number can be multiplied only when you will get some few electrons when light is incident on cathode. But if this watt function of the material is not suited for that particular wavelength, then these electrons cannot be ejected, and therefore you will not get any electron. And this resulted in no electrons and therefore no amplification. So therefore, uh, if you want to detect wavelength like 1310 nanometer or 1550 nanometer, then this photomultiplier may not be suitable for this detection. So then the question is, if you are not able to use this photomultiplier for this range of wavelength, is there any photo detector by which you can detect this type of signals? Then the answer is yes. And this is possible by using what is called as the internal photoelectric effect. Now, as I said, in internal photoelectric effect, you have to use a semiconductor, and when you will shine light to a semiconductor, then there will be electrons and holes which will be generated. And now what you have to do is, instead of allowing these electrons and holes to recombine, you separate these electrons and holes and allow them to flow in the external circuit to give some amount of current. So therefore, the number of electrons and holes which are produced in this semiconductor is directly proportional to the amount of light which you have incident. And the amount of electrons and holes which are produced is also directly proportional to the current which will flow in this external circuit. And therefore, the current which you are measuring is a direct measurement of the amount of light which you have incident on this semiconductor. So this is the basic principle of light detection in a semiconductor using this internal photoelectric effect. But then there is a problem with this, simple PN junction. We have mentioned while we are discussing about these sources that a simple PN junction is not suitable for this light emitting diode or laser diode, and therefore we have gone for what is called as this double heterostructure. Similarly, if you have a simple PN junction, it is not suitable for detection of light. Now, see, when I say that when you will shine light, then the electrons and holes are produced, then you have to ensure that the electrons holes do not recombine, because if the electrons and holes will recombine, you will get light. So I do not want that these electrons and holes to recombine and to produce light. But what I want is the electrons and holes should be separated and should flow in the external circuit to give some amount of current. And this is possible when you will give a reverse bias to this PN junction. So therefore, we can say that a reverse bias PN junction can be used as a photodetector. So source is a forward bias PN junction, whereas detector is a reversed bias PN junction. Now, coming to the again the structure of this detector, as I said, a simple PN junction cannot be used as an effective photodetector. This is because when you will shine light, essentially you are shining light in the active region, and the electrons and holes are generated, right? Now, the number of electrons and holes which are produced in this middle or the active region will try to move in the opposite direction so as to flow in this external circuit. So therefore, when the electrons will move in this material, some of the electrons will be absorbed by this material medium. This is the basic property of any medium. So therefore, maybe you have produced a number of electrons in the active region, but finally, when the electrons will reach the end of this end region, the number has drastically, might have drastically decreased. For example, suppose I have allowed this light to incident here and assume that there are 100 electrons which are produced. But when this 100 electrons which are produced and you are separating these electrons by this reverse bias voltage, they will flow along this path, that means along this material medium, and therefore some of the electrons will be absorbed. So therefore, you may get here 80 electrons or 75 electrons rather than the 100 electrons which you are producing here due to this light which you have incident here. So therefore, the efficiency of this detection has decreased. Then is there any solution for this? This solution is to increase this, the depletion region or the active region. Now, if you can increase this active region and at the expense of this, N region and P region, then what will happen is this. For example, I have I have increased I have increased this active region at the expense of this N region and P region. Initially, N region was up to this and P region was up to this. Now what I did, I have increased this active region, okay, and I have decreased this N region and P region. Now let us say if you have these electrons and holes which are produced in this active region, there will only flow for a short distance along this N region. So therefore, there is less probability for absorption. That means whatever number of electrons which you have produced in the active region, almost same number of electrons will reach at the other end of this PN junction. And another important point which you have to also understand, see, when you have a PN junction, in fact, a field is created along this junction. The field which is created along the junction is important in the sense this field is responsible to separate these electrons and holes and finally allow them to flow in this external circuit. Now, if you will see this electric field which is produced in this structure, then the electric field is very high in this intrinsic region, right? That means when you have formed a structures like this, the structure is called as the pin structure because this region, the active region, is very lightly docked. Therefore, this is something like an intrinsic region. So the intrinsic region is dominated here. So this is your P region, this is the intrinsic region, and this is the N region. So now, with this design of the structure, the electric field remains very high almost in this region and becomes zero, of course, at this point. That means here and becomes zero at this point. That means when you will allow this light to incident here, then the electrons and holes will be generated and the electrons and holes will be affected by this high electric field or strong electric field. And due to this strong electric field, the electrons will be separated very quickly, and therefore there is less chance of absorption. See, suppose the electrons will reach here with very small velocity, then the electrons will take more time to cross this region. So if the electrons will take more time to cross this region, then definitely the probability of absorption will be more. Now you have done two things. First of all, you have decreased this distance through which the electrons will travel and will reach the other end. And also we have decreased the time for the flow of electrons in this region by increasing this velocity of the electrons when it will reach at this particular end. And this is possible by increasing this electric field. So therefore, by increasing this velocity of the electrons, you have decreased the time of transit in this region, and also you have decreased this, distance along which the electrons will travel. So by doing these two things, we have reduced the probability of absorption of electrons while moving to this other end, and therefore the number of electrons which you have produced with the incident of light, the almost same number of electrons will reach the other end, and therefore the efficiency of this structure, which we call as pin structure, is very high. So therefore, we can use a pin structure rather than a simple PN junction for a photodetector, right? And in fact, this is the structure of a pin photodiode. As you can see, the pin region is there, and this pin region is grown on a substrate. So this is the indium phosphide. I was talking about the structure for a LED. You can see this is indium gallium arsenic phosphide. And if you use this is indium gallium arsenide. So if you are using indium gallium arsenide, the other layer may be indium phosphide, because the lattice constant of indium phosphide matches with indium gallium arsenide. So this is the substrate where you have to grow these different layers of pin structure, and then this metallization, and this is where the light enters into this, and there will be electron hole generation here. Then if you will give a reverse bias, then the electron holes will be separated, will reach the other end of this structure very soon. There is less probability of absorption. Therefore, the number of electrons which were produced in this region almost matches with the number of electrons which reach the other end, and therefore the efficiency of this device, of this structure, is expected to be very high. So this is how we have explained the principle of photodetection in a pin diode. And uh, in fact, these are the different parameters which are associated with this pin photodiode, like wavelength, responsibility, efficiency, dark current, rise time, bandwidth, and bias voltage. And next, we will go to the characteristics of this pin photodiode. And this is actually the VI characteristics. As you can see, in this region, this current is something like this. And when you are increasing this power, then this current is gradually increasing. So let me tell you here that if you are, using this photodiode, pin photodiode, this will work in this region, particularly this negative region, reverse bias region. And if you will use this in the positive region, this will work as a photovoltaic or a solar cell region, something like that. So we are not interested in photovoltaic in this particular syllabus, and therefore we concentrate on this photodiode. That means the current conversion of current from this light. Okay. Now this is all about your pin photodiode. As I mentioned, there are different modes which I have already mentioned. Then the next thing which we will discuss is about what is called as the uh, response time. And this response time for this actually pin photodiode can be expressed in terms of this relation. This is something 2.119 into RL into CD, and this is actually your the value of TR. And therefore, if you know the value of TR, as you have mentioned in the last lecture, then you can calculate this frequency or the maximum frequency for which this detector will work. As I said, you cannot use this, detector for any frequency of the signal. So if you want to know what should be the maximum frequency up to which the detector will work, then you have to use this relation like F3B is equal to 1 by 2 pi RL into CD, where RL is the resistance here, the resistance of, in fact, this is the load resistance, and CD is the capacitance of the diode which is formed here. So this actually the value of resistance and the value of capacitance will decide the maximum frequency up to which the the detector can be used. So this is all about this spin photodiode. Then what we will do next is we will try to understand another like structure which is similar to this photomultiplier. I have mentioned that vacuum photodiode is not efficient in the sense the current which will be produced in a vacuum photodiode is very small. Whereas if you use photomultiplier, then the number of kilotons can be increased, and therefore the current which will flow in this external circuit is something m times more than the current which will flow in a vacuum photodiode. As I've said, m is delta to the power n. Similarly, is there any structure in case of this semiconductor diode or based on the internal photoelectric effect which will act similar to this photomultiplier? The answer is yes. See, the structure is what is called as avalanche photodiode. So in that sense, you can compare this pin diode to this vacuum photodiode, and you can compare this avalanche photodiode to this photomultiplier. Now let us try to understand how this multiplication of electrons can be done using this avalanche photodiode. Here, of course, you are not using any denote as you have done in case of photomultiplier, but here you have restructured this pin photodiode. Now, how you have restructured here? Here, instead of taking a simple p-type of semiconductor, we have used a heavily doped p-type of semiconductor. Similarly, this side we have taken a heavily doped n-type of semiconductor. Then this is another layer, extra layer, which is called the p-type of semiconductor. So intentionally, I have formed a junction between this p-type of, this is moderately doped p-type of semiconductor, and this is heavily doped n-type of semiconductor. So when you will have a junction between this moderately doped p-type of semiconductor and heavily doped n-type of semiconductor, then you will see or you will find, can show that there will be a enhancement of electric field in this region. Basically, corresponding to this junction, you will find that suddenly the electric field which was there in the intrinsic region has increased. If you see this electric field in this intrinsic region, this is also high, but the value of electric field is still enhanced in this junction between this P and N plus type of semiconductor. Then what is the benefit of having this type of variation of electric field? Now, as you can see here, the electric field is remaining something flat in this region, though this is not also small. This electric field is high, but it is remaining flat. But when you are reaching this region, then suddenly the value of electric field has enhanced or has increased. Now, what will happen is something like this. Suppose you put light here in the intrinsic region, then the electrons and holes will be produced, and then the electron and holes will, the electrons will be subjected to this high electric field, and therefore they will try to escape out of this with large velocity or very more velocity, because the electric field is high, they will be accelerated, and therefore the electrons will try to escape out of this with high velocity, right? Now, then when these electrons will reach here, then the electrons will be suddenly subjected to further, more electric field, further high electric field, further strong electric field. So this will increase the velocity of the electrons further. And when these electrons will gain sufficient energy, there will be a accelerated to a very high velocity. They will get more amount of energy. So with this amount of energy, the electrons will try to collide with other neighboring atoms to knock out the electrons, the core electrons. As a result of which, you will find that the number of electrons will increase. For example, the first electron is accelerated to a very high velocity, then the energy is sufficient to collide with the neighboring atoms to knock out these core electrons. As a result of which, let us say you will get, let us say, 8 electrons. Now, these 8 electrons will be again subjected to the same high electric field, and therefore they will be accelerated, and you will get the very high velocity of the electrons. And this 7 plus 8, 8 electrons will be again colliding with another 8 atoms nearby and will produce further electrons. And these electrons will be accelerated to a very high velocity and again will collide with other neighboring atoms to produce further number of electrons. So this process is actually called as avalanche. And due to this avalanche, you will see that the number of electrons will go on increasing, just like you are using denotes in case of your photomultiplier to increase this number of electrons. So here you are suitably structuring this region to make this electric field intense so that the number of electrons which will be produced will be increasing, and this is process by which you are increasing this number of electrons is called as avalanche, and therefore this diode is called as avalanche photodiode. So if you compare this, current, again, the current will be definitely more in case of avalanche photodiode compared to this, your pin photodiode. So this current comparison, you can make it here. For example, as I have said, if eta EP by HF is the current in case of a pin diode, then in case of your APD, your current will be m times more than that. That means m into eta p by hf, where m is decided by this factor. The gain in case of your APD is decided by this factor. So this says that the current in case of APD is m times more than the current which is flowing in case of your pin diode. And this is about the responsibility. So the responsibility also will increase m times, and therefore the avalanche photodiode is a better detector for this detection of light. So this is about the multiplication gain and the 3 decibel bandwidth. And as you can see from this graph, when this multiplication gain is increasing, the 3 decibel bandwidth is also decreasing. In fact, initially it will increase, and then there will be saturation, and thereafter there is a decrease in this value of 3 decibel bandwidth. So there should be a compromise between the multiplication gain and the maximum frequency up to which you can use this photo detector. So these are some of these materials which are used for the photo detection. In case of APD, corresponding rise time, wavelength, responsivity, and dark current. And this will give you an idea about the different materials which are used for avalanche photodiode. And I think we will end here, and we will discuss further maybe in the next class. Thank you very much, and we will continue this lecture in the next class.